Welcome back to yet another video on our channel Euclid Mathematics. We have started lecture series on CSIR NET SET Gate previous year solved question paper along with their topics. So here in my today's video, I'm gonna explain to you all one of the question. It is from CSIR NET previous year question paper, which asks for 4.75 marks. That means multiple answer question. Okay, now let's read the question. I'm going to explain to you all detailed solution for each and every option. Now let's read the question here. So here in our question we have given f be an entire function, then which is a correct option. So we have four options given and we have to find out whether which one of the option is correct. Okay, so first option is given f is a constant if range of f contain in straight line. Okay, second option, if f is a constant if f has uncountably many zeros. Third option, if f is a constant if f is bounded on a set given z belongs to complex and real part of a z lesser equal 0. And last one, if f is a constant then real part of f is a bounded. Now let's start our today's solution. I will explain to you all each and every option in detail because this one is a multiple answer question, so we don't know one option is correct or more than one is correct. So here our first option, it says that f is a constant. Okay, if we have f constant then range of f contains straight line. Okay, and along with we have given f is the entire function, so we have f entire function, f entire is there, plus f is a constant. Okay, f entire is given, f is a constant given. Okay, so try to remember one theorem. Whenever we have to find out the points from some certain interval or some certain plane, so we always use like a Picard's theorem. Picard's theorem is useful here for finding whether first option is correct or not. Okay, so Picard theorem, it says that the range of a non-constant entire function can skip at most one point. Okay, that means the range, suppose consider this one is the range for non-constant entire function need to be a non-constant and entire. Okay, but we have given constant function and entire function. Okay, so we have here non-constant entire function can skip at most one point. So meaning here if we have one point here, okay, so the range, this is the range of a non-constant entire function. Here we can skip only one point in our range of a non-constant entire function. Only one point we can skip it here. Or vice versa, if that range of a non-constant function can skip more than one point, like 1 point, 2 point, or more than 2 point, can skip more than 2 point, then it become constant function. Okay, so what is the another form of Picard theorem we can see here? If a range of a non-constant, if a range of a constant function skip more than 1 point, okay, whenever f is the entire. Okay, so that means if function is a constant then its a range can skip more than 1 point. Okay, now let's see how the first option is correct here. Here is the statement of Picard's theorem I written. The range of a non-constant entire function can skip at most 1 point. Okay, only 1 point, maximum only 1 point it can skip. But if it can skip more than 1 point, then it is a constant function. Okay, so here we can see I given one small short example here, like a complex. An example, it is z and sine z. Okay, so it is having a range whole complex. Okay, z, it is a polynomial function, can be defined for infinitely many numbers, like any number you may select from complex. Okay, so here z is a non-constant entire function, which can shows that here its a range cannot skip any point, it gives all point in our range. Similarly for sine z also, that means it defines for all the points over here. Now second, complex minus singleton z1. Okay, that means here we can see z1, that means if we put z is equal to 0, so our function, we do not want that z is equal to 0. Okay, so e raised to 0, which is a 1, so we do not want this one. So complex minus z1 and 0 we do not want it into a range, so we can skip 1 point, maximum 1 point. Here I skip 1 point only as a 0. Okay, so it is a non-constant, e raised to z is always non-constant and entire function. Okay, these types of the counter example are more than sufficient to eliminate these options. Okay, now first option here, f constant if range of f contains straight line. Okay, if range of f which contains straight line, that means we have range here and which contains straight line. So how many points which lies here in a straight line? Infinitely many points which lies here in a straight line, because we are looking under complex plane. Okay, always remember, here we are always looking under complex plane. So if we plot any line in our complex plane, so each which can contain infinitely many point, that means it cannot have other point from other side of the plane. Okay, so here we can see in our plane I just drew one line here, so it contains infinitely many point, but what about for other point? Those are here other side of that line. Okay, so these are point which not coming here in this line, so we can say it here that line can skip infinitely many point. Okay, if this line can skip infinitely many point whenever it is possible when function is a constant. If function constant, then line can skip infinitely many point, and if function non-constant, then line cannot skip any point. Okay, just maximum it can skip one point. So here in my solution of first option I written here f is entire, then domain of f it is whole complex plane. Okay, whole complex plane, and within that complex plane if we drew one line. Okay, if I drew here already. Okay, one line, single line, that line can skip infinitely many point from our complex. Okay, f is the entire and domain become it complex number. So here I plot this, drew this figure here. You may see this is the complex plane, this one is the straight line. Okay, so it is domain whole complex plane here. This is the straight line which do not belongs here remaining point over here. Okay, so straight line here, we cannot contain other point. So that's why we say that the function, okay, the straight line which is a constant. Okay, so that means our first option which is correct. Okay, so what we have here, range of a range can skip uncountably many point here, uncountably many point. Then by Picard's theorem we can say it here, f is constant. If it cannot skip one maximum one point, it can skip one point or it cannot skip any other point, then we say that by using Picard's theorem our function is a non-constant, but it skip infinitely many points. That's why another statement of a Picard's theorem, it says that f is a constant. So our option number first, a, f is a constant if range of contain in straight line. Okay, so obviously it is true because it skip infinitely many point. Okay, so first option is a true over here. Now let's start second option. F is a constant if f has uncountably many zero. Okay, now simple counter example you may select here. Okay, if f is a constant, if I consider f is a constant like a f which is equal to c. Okay, so f of z I consider here c. Okay, like f of z which is equal to c here. Now, if f is constant, then it can skip uncountably many zeros. And when we get the zeros from our function, when we differentiate that function nth time, and whenever the differentiation it gives us a zero, then we say that it is a zeros of a function. Okay. Okay. So differentiate that f of z is equal to constant. So f dash of a z which is equal to differentiation of a constant function always gives zero. Again, differentiate one more time, f double dash of a z, again 0 constant, 0 is also constant, then differentiation of 0 again 0. So if we take nth differentiation of our z, it gives us a 0. Not only nth, you may go for any differentiation of a constant function, it gives us a 0. So if f is a constant, then zeros when we differentiate that function we get it here. Then if we have f has uncountably many zeros, so obviously it is true because I consider f as a constant function, then differentiate it, you will get the infinitely many zero, uncountable many zeros. So our option number B, which is correct. Okay, so you may select any constant function, as I selected f of z is a c. So you may select f of zi as a 0. So you will get the differentiation 0 at the end. Okay, everywhere. So now let's move for the option number third. F is a constant if f is a bounded on interval z belongs to complex and real part of a z which lesser equal 0. Okay, that means we have given f is entire. Now again we have to consider f is bounded. Okay, and we have to show that f is a constant. Okay, what we have given in our question, f is the entire. Okay, now let me explain with some short form here. So here we have given f entire. Okay, f is given entire. Okay, again we have given f is bounded plus f is bounded. F is entire and f is bounded, and one more condition we have here, z belongs to complex. Z belongs to complex such that real part of a z, real part of a z lesser equal 0. Okay, real part of a z means if we have f of z as u plus iv, then u is a real part and v is a imaginary part. Okay, so u is a real part, v is the imaginary part. Okay, and what we have given, f entire is already in question, f is bounded here, and the real part of a z, that means real, that means u lesser equal 0. Okay, this means u lesser equal 0, and then we have to prove that f is a constant. Okay, f is a constant. So consider some counter examples. Okay, any counter example that can satisfy f is entire and f is bounded. Okay, f entire and f is bounded, and prove that f is a constant or non-constant. Okay, so let me select one counter example for this. So here one of the most famous example we always consider here, which is the entire always. So in an entire complex plane, so f of z which is equal to e raised to z. Okay, so I consider here f is the entire, f of z is equal to e raised to z. If we have second condition, f is bounded on this interval. Okay, that means the value for here power of a z u which is 0 or smaller than 0. Okay, so I am having f of z is equal to e raised to z, and we know that z can be written as x plus iv, x plus iy, or u plus iv. Okay, so f of z I written here as a e raised to x plus iy. Okay, okay, so I consider entire here, and let's define second condition over here. Okay, so f of z is equal to e raised to x plus iy, that means f of z which is equal to e raised to x into e raised to iy. Okay, base same, then we can add their power. Okay, so take modulus from both sides, so modulus here, modulus here, modulus here. Okay, so e raised to x, okay, that means e raised to u, like I consider u here and x here. Okay, so e raised to x need to be a 0 or smaller than 0, then f is here as bounded. Okay, only for this condition f is bounded. So what is the value for e raised to iy, modulus of e raised to iy? Okay, modulus of e raised to iy we write as the e raised to I theta. Okay, e raised to I theta can be written as e raised to I theta cos theta plus I sin theta, cos theta plus I sin theta. So apply over here e raised to I theta iy, that means cos y plus I sin y. Okay, now further simplified it. So modulus of x plus iy, how we write modulus of x plus iy? X plus iy. So modulus of x plus iy can be written as square root of x square plus y square. Okay, when we take their modulus. So similarly apply over here. So we can write here cos square y plus sin square y. So square root of 1. Okay, so it gives value 1. Okay, so the modulus of e raised to iy having here value 1. Okay, and e raised to iy possesses value 1, and e raised to x keep it is same. So f of z can be written as only here modulus of e raised to x, okay, into e raised to iy is 1. And here f of z I got it here e raised to x when x need to be smaller than 0. That means the real part need to be smaller than 0. So here I got the second condition, which is f is entire already. If I applied second condition, f is bounded on this interval. That means the only the real part, which is x, need to be a 0 or smaller than 0. But as we have here f of z, which is a non-constant, e raised to x is a non-constant function. Okay, but we have given f is a constant. How it is possible? I consider here f is a entire. Second, I applied second condition, f is bounded on this interval. Okay, so all these condition I applied over here. So as per the option, we have to get it here f as a constant. But here we got the other condition, vice versa condition, that f of z e raised to x. Okay, it's a contra positive condition we found it here. That means e raised to x is a unbounded function. Okay, unbounded means it is a non-constant function, and we have given in our option f is a constant. Okay, so here we can say directly option number C, which is a wrong. Now let's move for last option. Here in my next part I explain here this step as it is over here. You may see this part. Okay, so now let's go for the next part. F is a constant if a real part of f is bounded. Okay, that means f is a entire given, real part of f is a bounded given, and we have to show that f is a constant. Okay, now we have one standard result that if we have function f function like f is equal to u plus iv. Okay, the real part is a u and imaginary part is a v. Okay, one of them, any one of them, either u or either v. Okay, you may select one of them. If it is bounded, one of them is a bounded, then we say that whole f is a constant. Okay, always remember this is very much important result. If we have function f is equal to u plus iv, then one of the part like a real part or imaginary part, one of them is a bounded. Okay, f is constant, then real part of f is a bounded. Okay, that means we have given f is the entire function and real part of f is bounded. That means real part means u is bounded. So I got the u, one of them is bounded. Then surely f is a constant. Okay, always remember f is a constant. So obviously option number 4 is coming true. So here I explained here f is a constant if real part of f is bounded. Okay, always remember what we have given in our question. In our question we have given f is the entire function, and here one more condition, real part of f is bounded, then we say that f is a constant function. Instead of a real part, if you get that here imaginary part is a bounded, then you may also say f is a constant. Okay, so function I consider is here f is equal to u plus iv. Okay, so this one is a standard result, is the entire function and either u or v, it is or here not and, or v are bounded, then f is a constant. Okay, this one is the correct option. So option number 4 is correct from our given question. So this one is the question from CSIR NET previous year question paper, completely based on Lively theorem and other related concept. I hope you all have understood my today's lecture. It is quite easy solution of our question. So even after, if you found anything difficult, let me know in the comment section. So thank you everyone. Thank you for my today's lecture.